Hello everyone, I am Parag N. Today I will be presenting my disease prediction project. This is did I using logistic regression. Let me walk through the whole section of my Jupyter notebook. First, I import the necessary Python libraries. These include the pandas, NumPy for data manipulation, Matplotlib and Seaborn for visualization, and scikit-learn for machine learning models like logistic regression, random forest, SVM, and KNN. These models. I also imported metrics like accuracy score, precision, recall, F1 score, and confusion metrics for my evaluation. This is my imported libraries. Then, then we talk about load and explore dataset. I loaded the diseases dataset using pandas. This is my dataset. I get it from Kaggle. The dataset containing a patient ID, medical information, age, gender, chest pain, like a lot of health categories. I used .info to check data types and null counts, describe to see statistical summaries, and .head to preview the first few rows. Then you can see it. Uh, uh, then we can see a data loaded successfully. This is my loaded data set. Rows 1000 and columns 14. Uh, then we talk about my section 3 is data cleaning. For data cleaning, first I remove the patient ID column because it is just a unique identifier that has no relationship with heart diseases prediction. Then I check the missing or null values. I used is null and some count missing values. Fortunately, this dataset was clean and with no missing values, so I didn't need to perform or removal rows. Then this is data cleaning steps we can see. Then the next one is exploratory data analysis. Mm, First, I visualize the distribution no target variable to check for class imbalance. This shows the many patients have heart diseases. Many patients have heart diseases. Uh, those who don't. Next, I plotted an age distribution. Histograms then see the age range. I also created the bar charts. These are my bar charts. I also created bar charts. Relationship between chest pain types and heart diseases. As you can see, patients with certain chest pain types have a higher likelihood diseases. Then we talk about the section 6. Section 6 is feature selection. For feature selection, I analyze the correlation and each features with the target variable. Features with a very low correlation were considered for removal. And this is my feature selection phase, keeping all features. Then outlier detection and handling. Mm, Next, I perform outlier detection and handling. Outliers are extreme values that can negatively impact the model performance. These are my outlier detection part. As you can see, some features like a cholesterol and visible outliers. I used IQR method to detect and cap extreme values. Mm, This is my outliers. Then we talk about section 6. Section 6 is data pre-processing. For data pre-processing, I perform feature scale. This is important because machine learning algorithms like logistic regression and SVM are sensitive to scale of features. This is my feature scaling code. This is the output of feature scaling. Uh, then I then we talk about section 8, train and test split. Before training model, I split the data into training and testing sets. I used 18% and 20% training and testing. Then we can see training set size 80% and testing set size 20%. Then we talk about my model training part. Now I trained the my group trained the four different machine learning models. I did logistic regression. Uh, then I check the overfitting. Overfitting happens when a model performs very well on training data but poorly test data. Uh, this model, we can see the training accuracy 95.62 and training accuracy 97.0. This model is not overfit. This is a very good fit. training and testing accuracy are close. This is a well generalized model. Then section 11 is comprehensive model evaluation. Finally, I performed the comprehensive model evaluation using multiple metrics. I plotted the confusion metrics for each model and visualized the positive and true negatives. This is that my visualization part. Then this is my model saving part.
I developed a machine learning model to predict heart disease using a decision tree classifier. I will go through each step of the process and explain what was done in each section. First, I loaded the dataset and examined its structure. I checked the number of rows and columns, data types, and displayed the few records to understand how the data is organized. I also reviewed the statistical summary to understand the range of values and check for missing values. Finally, I analyzed the distribution of the target variable to understand how many patients have heart disease and how many do not. Next, I cleaned the dataset to improve data quality. I confirmed there was no missing values and removed duplicates records if present. I also handled unrealistic values such as zero values in features like blood pressure and cholesterol by replacing them with median values. This ensures the dataset is more reliable for model training. In this section, I explored the data to understand relationships between variables. I used a correlation heat map to identify how strongly features are related to the target variable. I also plotted feature distributions to observe how values are spread and identify any unusual patterns. Additionally, I visualized the target distribution to check whether the dataset is balanced. Here I selected the features to be used for the model. I removed the patient ID column because it is only an identifier and does not contribute to prediction. All remaining clinical features were kept as they are relevant for predicting heart disease. Next, I detected outliers using the IQR method, which identifies values that fall outside the normal range. I visualized these outliers using box plots. Instead of removing them, I handled them using capping where extreme values are limited to a reasonable range. This reduces the impact of outliers while keeping the dataset size unchanged. In this step, I prepared the final dataset for model training. I separated the input features and the target variable. I also checked the categorical variables, but since all features were numerical, no encoding was required. Feature scaling was not applied because decision tree models do not require normalization. The dataset was split into training and testing sets using an 80:20 ratio. Stratification was applied to maintain the same proportion of classes in both sets. This ensures that the model is trained and evaluated fairly. Here I train the decision tree model using the training data. The model learns by splitting the data based on feature values. To avoid overfitting, I control the tree depth and set minimum sample requirements. I also use balanced class weights to handle class imbalance. I visualize the decision tree and to understand how it makes decisions. This is the full tree of decision tree. It shows all decision paths, while this is simplified version. This is the simplified version. It helps clearly understand the main rules. In this section, I analyze feature importance to identify which variables contribute most to predictions. Features with higher importance values have a greater impact on the model's decisions. This is the feature importance graph. As seen, this slope is the very important for the key as a key feature. In overfitting check, I compare training and testing accuracy to check for overfitting. The training accuracy was 96% and the testing accuracy was 97%, as the This shown accuracy gap was 1%. So since both values are close, the model generalizes well and does not overfit. The model was evaluated using accuracy, confusion matrix and classification report. The model achieved high accuracy as this shown. Testing accuracy was 97%. The confusion matrix shows how many predictions were correct or incorrect. Precision, recall and F1 score provide a deeper understanding of performance. Recall is especially important here because missing a patient with heart disease can be risky. The trained model was saved using Joblib and Pickle. This allows the model to be reused without retraining. Features names were also saved to ensure consistency during predictions. The model was tested using new patient data. In summary, the model was built through data understanding, pre-processing and training and evaluation. The decision tree model achieved high accuracy and provided interpretable results. It can be further improved using larger data sets or more advanced models. Thank you.
In this part of the project, I will explain my contribution, which is developing a random forest model to predict heart disease using a cardiovascular dataset. The main objective of this model is to identify whether a patient is likely to have heart disease based on medical attributes such as age, cholesterol level, blood pressure, and other health-related factors. For this task, I used a random forest algorithm because it is highly accurate and helps reduce overfitting. First, I imported the required libraries including Pandas and NumPy for data handling, Matplotlib library and Seaborg for visualization, scikit-learn for building the machine learning model. Next, I loaded the dataset and performed an initial overview by displaying the first few rows. Checking data types and verifying that there were no missing values, the data contains 1000 records and the 14 columns. It was clean and consistent. After that, I performed exploratory data analysis or EDA. In this step, I use visualization like histograms and correlation heat maps to understand the data. From these analyses, I found the most important features related to heart disease were slope, chest pain, number of major vessels, resting blood pressure, and resting electrocardiographic result. Next, I performed feature selection. I removed the patient ID column because it is not relevant for prediction and kept 12 important medical features. This helped improve accuracy and reduce unnecessary complexity. Then I moved an outlier detection. Using boxplot and the IQR method, I identified 235 outlier rows. After removing these, the dataset size was reduced from 1000 to 765 rows. This step improved data quality and model performance. After that, I prepared the data for training by defining the feature set X and target variable Y. Then I split the dataset into training and testing set using 80% and training to 20% for testing. Then I trained the random forest classifier. I use control hyperparameters such as 10 trees, maximum depth of tree and minimum sample per split and leave to prevent overfitting and improve generalization. After training, I used the model to make prediction on the testing dataset. Now coming to the most important part, model evaluation. The model achieved training accuracy of 96.73% and a testing accuracy of 98.04%, which shows excellent performance and good generalization. The confusion metric result showed 62 true negatives, 88 true positives, only 2 false positives and 1 false negative. This indicates that the model makes very few errors. From the classification report, precision is 97.78%, recall is 98.88%, F1 score is 98.32%. These values show the model is highly reliable in predicting heart disease and maintain a strong balance between accuracy and sensitivity. In conclusion, the random forest model performs extremely well with highly accuracy and minimal errors. This system can be useful in real-world healthcare application for early detection of heart diseases. Thank you. That was my contribution to the project.
Okay. Hello, good morning. I am Kamil Derwan and I am choosing support vector machine to perform this hard disease prediction problem. That's actually why I am choosing support vector machine because of that hard disease. Basically, these problems decides patient have a heart disease or not. That means this problem is a classification problem, and support vector machine model is perform very well on the classification problems. Support vector machines also support vector machine find out best boundary line and best bound line, that means hyperplane. So here why I choose support vector machine to perform on this data set. When we considering about this data set, there are basically 14 features, that means 13 features and one categorical variable, one target variable. That target variable decide is this a disease patient or not, and there are a mix of numerical and categorical features. When we after doing a data cleaning process, that we can see there are no duplicate rows. That ensures the integrity of this data set. And also when we consider about the target variable distribution, there are 580 as a heart disease, and 420 20s for not heart disease. This is a very good scenario, and that shows the integrity of the data set. When we considering about the model training and splitting to evaluate how well our model perform unseen data, we use train test split. We allocated 18 percentage of data to the model and kept 20 back for testing process. And also looking at the confusion matrix, we go through the confusion matrix. Here is the confusion matrix. And the classification record, we see a balanced performance for class 1 disease. The recall was 0.94 for the recall, and the meanings the model is highly effective and identifies patients who actually have the condition, a critical metric in healthcare to avoid a missing diagnosis. When we considering about the confusion matrix and the details classification report showing precision as a 0.9753. It's a very good, that ensures this is a very good performed on the support vector machine, performed on the data set. Finally, we test the model with the simulated patient data. For instance, 53-year-old male with specific vital was correctly predicted to have heart disease with a 99 probability. In conclusion, by following rigorous pipeline of cleaning, scaling, and training, we have, when we considering about the which scaling, we use the standardization. We have developed an SVM model that offers high accuracy. The high accuracy is the very high accuracy is 0.9066. It is very important because of this kind of scenario. Here we testing about heart patients, so accuracy is the most powerful weapon when we considering about this scenario. So according to these classification records, we can say we have developed an SVM model that offers high accuracy and actionable probabilities for cardiovascular risk assessment.